All right, shall we continue? Well, since nobody complains, I'll just continue. Let me have a quick look. Right, finally, more exciting things for the maths. Diagrams and graphics. What are we going to do with those? How are we going to make those accessible? How do we get them into an accessible document? What are the techniques for that? Well, first of all, we should distinguish things when it comes to diagrams and graphics. We've discussed that already in a previous lecture, but I'll just want to emphasize that again. That there's always two kinds of graphics that you can think of. One are just normal images, as you get them from your camera, as you get them from other sources, like you know, from your phone and whatnot, and they're generally what's called bitmap images or raster images, which means that they consist kind of, think about them as a rectangle with pixels, which are either black and white pixels or color pixels, and they normally are in there kind of in a compressed version. And you've got formats like JPEG, which is particularly strongly compressed index color scheme version. PNG, which is the successor of the GIF format, which is more true color encoding of images. And then you've got things like TIFF, which some of you might be familiar with. In particular, that's a standard format for scanning documents into high quality scanning, and it's a lot more resolution. Can carry a lot more resolution than most of the other formats. The problem with that is always their fixed size. They can't really scale, not zoom. So think about it this way: you've captured them once, it's frozen. The pixels are in a way frozen, and you can't get more detail. All you can get is kind of a larger version of the same content. Meaning that if you blow it up too large, it gets very ugly. It's like, you know, if you have a snapshot of your favorite animal or of your favorite place or whatever, if you then have it in a small format, it looks good. If you then blow it up in order to put it on the wall of your office, it often looks grainy and ugly. What's the way around it? Well, something that can actually work with size, and that can not only scale up smoothly, but also potentially add more details if and when they are necessary or possible to add. Right? And some of that's traditionally called vector graphics. And there's vector graphics, there's plenty of formats. The one we're really going to look at is going to be SVG, which stands for Scalable Vector Graphics. There's others. There's a proprietary from Microsoft, which is called WMF. And then there's PGF, which is a standard vector graphics format inside LaTeX, the LaTeX converter, particular for packages like Tixi. And then the classical format is, for instance, encapsulated PostScript, EPS, which was the vector format for PostScript converters and PostScript formats, which was the predecessor of PDF. Right, so how do we make them accessible? Well, traditionally, or what is sufficient according to WCAG regulations, is to provide alternative text. So you can add, so if you have, say, a graphics on the web page, or also just a graphics in a PDF document, you can provide alternative text that should explain the graphic. Obviously, that's generally not enough. It's usually enough if you have some sort of information-free graphic. Say you have 3 cats in the graphic, then it's sufficient to say, well, there's 3 cats, maybe 3 cats, whatever race the cats are, and maybe also how they, do they sit next to each other or on top of each other or whatnot. But when you talk about more complicated graphics, in particular diagrams or illustrative graphics which should convey some sort of an information, which are in many ways information rich, then just providing alternative text is generally not enough. Also think about alternative text in terms of fixed length. So generally, I think it's 128 or 160 characters that alternative text is supposed to be at most, which is the average size of a tweet. And you can't really explain a lot in a tweet, as we all know. And that's why people retweet all the time or reply to their own tweets all the time, right? And you can't really do that if you want to do that in a document. So an alternative there is that you provide more description in a particular paragraph in the page, which is generally good and acceptable authoring style. And you've got various ways to deal with that. Via using things like ARIA labeled by or ARIA described by that allow you then to direct accessibility or assistive technology to that particular piece of content. Right. Okay, I've got some examples here, but I'm not sure whether those are really right. So just a quick difference between some of these examples here. Here's an image of a box plot on Wikipedia, which is just an image. So this is although it's derived from an SVG, as you can see, maybe if you can see the image, this is a bitmap graphic, meaning that it gets grainier and grainier the larger we make it, and it gets uglier and uglier the larger we go. Also, if we change, for instance, the background, I don't think that will change. I'm not sure whether that will change the background as well. Let's do that. Well, it does. It does. Well, so at least it hasn't. It's not opaque. But you can now see, for instance, that the experiment down there, you can hardly read that anymore at this zoom factor. A proper SVG for something like this is, I believe I've shown that before, is, for instance, a high charts box plot, which not only is SVG and therefore scales nicely, and you can make it as large as you like, and you can still read it very well, but it also contains a lot of information for those. If you can see that on the screen here, let me again change the background color, just so you can, so things get nice. And you hover over things, it tells you what this is. So this is an outlier, and this here is a box plot with a particular observation, maximum upper quartile, and whatnot. And that's exactly the information that you want and that you might need exposed at some point. Right. Right, so what's scalable vector graphics? So in order to be able to understand what we can do with it, it's always a good idea to understand what is the basic technology and what does it allow for. So obviously it's a vector graphic, so the idea is not to actually have a drawn image which you capture and then display, but what you rather do is you have a declarative language which allows you to formulate the components from which your graphic has been built. Then what these components can then be grouped together and can be described. And then you have all kinds of fancy things you can use in SVGs, particular things like animations and foreign objects, and you can include all kinds of additional information, particular because unlike normal HTML, SVG allows you to use namespaces. Right? Namespaces means that you have kind of your own format in order to express something in an XML document without having the fear that you might interfere with something somebody else has already put in there, or with some of the standard components of that particular dialect of XML you're using. So what are the basic components of SVG? Well, the basic components are, of course, drawing components. So things that draw visual elements on the screen. Now, so you've got things like circle, line, rectangle, ellipses, but you also got things to draw more complex elements, polygon, polylines, and general paths. Path is pretty much the most general way in which you can describe curves, and which allow you to then build things, build arbitrary structures in many ways, right, that go beyond rectangles and circles. You've got text elements, of course, and then you've got various ways of styling these things. So you've got particular styling elements and how to fill things, and you can do the same thing with attributes. So for instance, you can say a polygon is something, you describe a polygon, whatever, six corners, you give the coordinates of these corners, and then you say, well, it should be this stroke width, meaning that the side of the polygon are being drawn at a particular size, and you can then fill it and do all kinds of things. Things effectively you are used to from your normal drawing program, you can specify with XML commands or tags and attributes. And that's not all. So now comes kind of the intelligent bits of SVGs. You can then use things like a grouping tag, and that's probably the most important for us, which is the grouping tag, just G, normal single letter tag, which allows you to group different components together. And it allows you to group different components together, not just once, but multiple times in a hierarchical form, right? So you can think about, trees, which structure more and more details, going from the root to the bottom and become more and more detailed. It also, since you've got pattern and simple elements, and as well as what's called the defs element, that's particularly exciting, which allows you to predefine an element that is not being drawn, and you can reuse that multiple times in your drawing, meaning that the same element can not only occur multiple times in the drawing, but also in different tag groups. So you can thereby have more complex structures than just a single hierarchies. And for accessibility, what's interesting are the so-called descriptive elements. You have a title element, which you can give to every single element in your tree, every single element in your SVG structure. And you've got a further one, which is description element, which gives more info, or should give more information. Think about it this way: if you're familiar with the ARIA, we've also already discussed the ARIA syntax. So there's the ARIA label, which just names a particular element, and then you have the ARIA described by, which tells you where the description or the more complex description for that element is. You can do the same thing in SVG, just that you put it straight with the element. So the title and the described by goes with the same element. Let me have a look. Is that? No, that's not the example. That's just the elements themselves. Right. Right. Finally, last thing about SVG components, and those are the advanced components, which are quite interesting. So you've got primarily ways to change how an SVG is being drawn using transformations. Transformations are mathematical transformations of vector elements. So that effectively goes down to that, we're having a vector graphic, which is a 2 to 3 dimensional vector space, depending on what kind of transformation you're using. And you can use the normal mathematical transformations on them. So you can have things like translations, scaling, rotation, and skewing, as well as composing all of these with normal linear algebra arithmetic, so just matrix arithmetic. And on top of that, you can then also animate all these SVGs. So animation, there's a bunch of things how you can use animation. A lot of them can be pre-timed, but things can also be bound with particular styling structures like CSS and others. So there's all kinds of nifty trickery you can do with SVG. Let's have a look at one of those. So this here is an animated.
One question.
Yes.
So when we sort of zoom in and when we make it small, the smaller items disappear.
Yes.
So when you want to draw the SVG, so you will also can draw it at different scales.
Yes. Well, if
what scale you are using for drawing it, relative scale.
Yes, you can scale that up if you like. Yes, but you can also say you can also have a command in there in many ways that allows. There's a switch command, for instance, which allows you to draw or not draw certain elements depending on particular conditions. One classical condition is, for instance, that you draw a label different depending on the document or on the language of the document. But you can also, depending on the CSS styling or on the scaling, whether something is being drawn or not. And that way you can kind of start hiding things, right?
Now, my question was related to when you're creating this diagram, and let's say you have elements of very different sizes, but then you're drawing it on the palette, you will like to use it at work at some sizes because you will not be able to handle it.
Oh, yes.
So you should be able, one can actually define what scale I'm drawing so that when it merges with rest of the elements, it automatically takes that.
Yes, that's. I'm not quite sure whether I've said no. I don't say that here. I think in the translations, but I'm going to mention that in a couple of slides.
Okay.
So there's different ways how to do translations, and in particular, there's the global way where you can kind of do translations applying to all elements, and then you could apply translations only to certain branches of your SVG, meaning that you can kind of have drawn elements. Some might be very large, some might be very small, but then you combine them in one SVG by doing different scaling or translation or whatnot on them, right?
Okay, so you do that at the time when you're putting them together.
Yes, exactly. and you can change that. You can change them programmatically and dynamically, right? That means that some things grow, others go smaller, or something of that nature. Well, this here is a very, very trivial or simple animation of the roots of Unity on a. Let me make that a bit larger. So what happens here is this is from the algebra book I've showed you earlier, and what happens here is that the roots of Unity are being drawn on the unit circle, right? So here you've got 1 omega. Omega stands effectively, what is that? Well, the square root of 1 plus I square or something. I don't know. Don't remember what omega really stands for. And I, so it's in the complex plane, and you draw the 8 roots of Unity around here, and the way that the animation works is the way it would be drawn, or most people would probably draw it on a whiteboard. All right, let me just run that again. So the x-axis comes in, then the y-axis comes in, the circle, 1 omega I, now omega to the power of 3 minus 1, omega to the power of 5 minus I, and omega to the power of 7. All right, going around in anti-clockwise along the unit circle. Oops, a bit large. And right. So SVGs. So SVGs, as I said, can be highly structured, but they also cannot be structured at all, right? And that is a problem. So we can do a lot with SVGs, and you can do a lot of things well, and you can do a lot of things badly. So I've put together a couple of points which define, in my opinion, at least badly. So badly means if, for instance, which is normally not the human being, but generally it's generators that automatically export graphics into SVG, do things systematically. What do I mean by systematically? Well, systematically means that you draw the visually or the visible elements one by one. You say, oh, line, 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 and then character, 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 you know, and place them where they should go, but thereby losing any relation those characters and lines might have together, for instance. Another thing is when you use things like global transformations. What are global transformations? That's what Bala just alluded to. Global transformation is that I have, say, a drawing of all my components, and then I apply a single transformation to that, right? Which either scales it up or translates in the coordinate system or does something like this. There's a couple of issues with that. First of all, that means all the things are effectively at the same scale, and it makes it difficult to say something is more important than others, but in certain contexts where you might want to increase the size of one component, decrease the size of another, as well as which is a way, for instance, to show semantics, and in particular to magnify elements that are important when we speak them, or when we discuss them, or when we in other way want to emphasize or highlight them. So ideally, a good SVG element should have grouped elements, semantically grouped elements, i.e. not just line, 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 but say, oh, line, next to it is that character, next to it is the other line, and these three things mean something together, so I put another group around it, and that's part of another group which contains other elements, and so on. So that's semantically grouped. They should all have an annotation in terms of titles and descriptions, giving them metadata, giving them landing zones in a way, so you can click on things, or you can see things, things can be properly outlined, and thereby the things transformation should be all local to the element. So the elements should be done in regardless of how they're actually being drawn, they should be transformed so they all fit together in that image. And I've got a couple of examples for that. Here's one example of a molecule. It's an aspirin molecule, and it looks good. Looks like aspirin. It's got line drawings. It's got a benzene ring. It's got all kinds of characters in there which represent atoms. Now I'll show you how the code looks like. Here's the code. And the code, for those of you who can see it, you will notice that although it is a XML element, there's hardly any indentation. Why is there no indentation? Because it's all just single elements lined up. So you've got a line, 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 and then you've got a bunch of text elements which are surrounded by rectangles. All right, and that's it. There's nothing else in there. So this is just, that doesn't give you any indication of what these things really mean. But if we look at these aspirin elements, these molecules, for instance, you see that there's a ring, and in this ring you have what's called double bonds, so parallel lines, and these things are important. They have a relationship to each other, and therefore should be grouped together. So let's have a look at a way. Oops. Didn't mean to do that, I think. Sorry, I've just lost my slides here. Where did they go? Oh, there they are. Yeah, let's have a look at a well-structured version of the same. If you can see the slides, here they are. Same drawing, visually exactly the same drawing. Now let's see what's under the hood. Under the hood, obviously, the source is different. If you're looking at the source code here, you can immediately see there's a lot of more indentation going on, because it's intended as it should be for an XML element, and it's not just flat. Meaning that you can see all these little grouping elements, and these grouping elements actually put together, and they have a title element. They represent a polygon, which we didn't even have in the previous element, in the previous in the previous graphic. And then you can see these things grouping together. Lines are grouped together, bonds, and you have two lines grouped together. They get a title called double bond, and so on and so forth. And every line here has not just a title, and it's grouped together, the single line with the title single bond, for instance, but it also has a polygon around it. And what does that polygon mean? That is an invisible polygon. It's difficult to see, obviously, without, I think, yes. So here's an opacity value of 0, meaning that it's effectively fully see-through. And that is what's called the landing zone. And that landing zone means that gives you now a means of actually finding this part in the drawn element. And then what else can we observe here? There's a different there's a daisy layer, so that's for daisy readers, so what to switch on and switch off. So that's all different namespaces. So there's actually 2 namespaces in there. And all that information in many ways makes that, of course, a much larger SVG, but also much more informative SVG. The major problem there is, where are we? Where are my slides? Here they are. No, that's not it. That's there. That, as I said, makes it quite a considerably larger SVG, meaning that if you use anything that tries to optimize SVGs, for instance, all this will get lost. And therefore, I've put a little warning here, beware of SVG optimization. It's a bad thing to do in general. If it comes to accessibility, it's really, really bad because they try to throw away everything they think, these optimizers, everything they think is not really necessary, often including title elements, grouping, of course, but title elements, description, and all of the above. So if you already have a bad SVG, can you do something to make it a good one? Yes, there's various tools to do that. But best one to use these days is probably Inkscape. Inkscape is an open source SVG generator drawing program. You can group elements, you can do all kinds of things. You can add titles, you can do you can add descriptions and various other things, and it has plenty of plugins and tools to work with that allow you to actually create good SVGs, even out of bad ones. Right.
You can existing SVG.
Yes. Yes, you can also
create one.
You can create one. There's also some tools out there. So I haven't really put any together yet for these slides, but there's other tools out there which allow you to transform existing images from bitmap images into SVGs, and there's different varieties. So the easiest way to do this is, for instance, by just putting in a single path, meaning that everything that's being drawn is going to be a single element, which makes it very, very difficult. Obviously, if it's only a single element, you can't really group anything together or describe parts of the element. There are some transformers out there which do a better job at identifying lines and characters, for instance, or at least allow you to split these things apart. There are plugins for Inkscape which allow you to do these as well. So we could do an entire new lecture just about SVG when it comes to these things. I mean, there's a lot of things to play with and explore and make good use of. Right. I'm again mindful of the time and that I'm, only half through my slides, so at least we'll have something to start next time. Let's talk a bit about output formats. So what can we actually generate from SVG? Obviously, we can draw them on the screen. There's a lot of drawing programs out there which allow you to draw, or drawing libraries rather, that allow you to draw SVGs in various applications, and obviously in particular on the web. And also in many EPUB readers, for instance. Not all of them, of course. SVG now is supported by all major browsers. It wasn't, for instance, the one that never supported it properly was Internet Explorer, but since that has been superseded by Edge, now all browsers really support full SVG. They don't. Not every single browser has a full implementation of the entire SVG stack. I think now that most of them are on WebKit and Blink. I think there's still some things missing in WebKit, but I don't want to lie here, but there were always some certain things which were missing, in terms of the CSS styling and so on. But in general, it's all very, very well supported these days. And but we can also generate a number of other output formats with SVG, and I'm going to talk probably in the next 10 minutes primarily about tactile, and there's also audio tactile, and then we're going to start discussing screen reading and sonification and other fancy things next Tuesday. Tactile graphics, of course, that goes partially back to some of the things we're currently doing in this project with the pretext, documents. But there's a number of there's also other packages which allow you to just take SVG graphics and put them straight to an embosser. What is interesting there is often that it's problematic to include the notation. So what I've shown here on that slide is this unit circle, or the roots of the unity on the unit circle in the complex plane, which I showed you earlier as an animation, but this time it's generated from the original LaTeX TXI code straight with Braille output. And the Braille output here is given in BRF, so that's ASCII Braille, which represents Braille characters, right? So as you might have seen previously in this transcription tool, where we can kind of enter ASCII characters and Braille comes out, and that's very similar. So the number sign 1 stands for Nemeth number sign, so that's, I think that's Braille cell 3456, and then 1 is Braille cell 1, yeah, and so it's Braille's number 0, etc. Now, what's the main problematic point about that is that now where the label is being placed is different from where you would place the label in normal output in LaTeX. So in many ways, the bounding box of the Braille cells obviously are not necessarily in the same place as the math formula. There's another issue to go with it, and that issue is fairly little on this. It's fairly well understood, but it's not a lot of people actually work on it. So, and that has to do with the actual Braille cells for reading, for transcribing either formulas or for transcribing text. If you have an SVG, think about it this way: an SVG is scalable, right? So it doesn't matter whether you print it or emboss it small or whether you emboss it large, right? So you emboss it on a small piece of paper, or you emboss it on a, say, A4 piece of paper. Now that's great. So that means your circle that you can actually feel becomes a nice and large circle. However, what happens to the Braille? Now the problem is, if you enlarge the Braille along with the circle, that means that the distances between the single cells, or the single dots in a single Braille cell increases as well, meaning that you can't really read that anymore, right? People are used to a particular size for their Braille cells. This is how they learn to read them. Now so you can imagine that there's in many ways you now have a graphics, an SVG graphic, which nicely scales, and you want to scale everything with the exception of these particular cells in there. And there comes the thing with the trick Bala had referred to earlier, or alluded to earlier, is that we can transform these things separately. In many ways, we do have transformations just on the elements that describe the axis and the circle, for instance. Those are being translated and those are being scaled, whereas the bits that contain the actual textual information, the Braille cells, do not scale. Right? There might still be a problem that you then might have to move them about in order so they don't overlap with anything that and stay in the right position at the circle. But these are all technical issues that need to be sorted out. But just to give you an idea how some of these things are being sorted out, here's an image. If for those of you can see it, this is, I think that's probably it's either Rob or Alexei Kolesnikov working on the actual embossed Braille cell, measuring with a ruler, how large are things apart. You can see this is the embossed circle here. If you can see that, you can see that some of it's not, the dots which represent the actual elements or the positions of the roots of unity along the unit circle are not necessarily as round as they are in the image. Neither is a circle. You can see the Braille cells there. You can see what's supposed to be arrowheads at some point, which don't always come out nicely. One major problem, of course, is that the resolution you have on screen is so much, it's by multiple orders of magnitude larger than what you ever can get with an embosser, right? So the resolution you can get with single dots is so much worse, meaning that things like circles already come out very, very jagged and in many places. Right. And I'm mindful that we're pretty much at the end of the time, so I'll stop screen sharing and I'll rather share some of these things live with you. Can you see me?
Yes. Yes.
Very good. I've showed you the I think I've showed you that algebra book earlier. This here is, if you can see that. You can probably not see the dot cells, but this is just the first chapter, the introductory chapter of that book in Braille. All embossed. It is probably about 30, 40 pages, just the single first chapter, with all the math formulas in there and all the text. However, none of the graphics. All the graphics are in a separate book. And that's the book. For those of you, I don't know whether you can see that. You probably can't see that. I think this way around is the right way around. That's mappings between two sets. I think that's one-to-one mappings, injective, surjective, one of those, and so on and so forth. And these are all just, again, first chapter only. All the figures in there, properly done. Yeah, here's the map of all the figures that you can actually see. I don't know whether you can see that.
Yeah, you can see that.
Right, and so yeah, right. So you can imagine it is a good, it is quite an endeavor to get this going. It contains a lot of interesting research questions as well, in particular for document generation. Right, and I think we'll start tomorrow with going over some of the more advanced things we can do with SVG.
It is on Tuesday.
On the web. Sorry.
Next Tuesday.
Yes, it's not tomorrow. Yes, I'm very confused. It's very. I'm glad it's Tuesday. That gives me a bit of time.
Even today on a Saturday, our attendance was lower. So I think if you do it on Sunday, then maybe only we two will be.
Yeah, then I'll talk to myself. I still appreciate everybody who showed up on the Saturday. That's certainly the case. Are there any questions?
Any questions, please?
Yeah, Volker, thanks for these diagrammatic representations. Actually, I was more interested, like, how does it work with the screen reader, particularly like when you make this SVGs and run it on a browser? and all that.
So this is my plot for Tuesday's lecture. This is where we're
Okay.
going to start on Tuesday, because that's
Yeah.
now effectively the
There's
next
all like
slide
mouse
I have.
overs and all that. You can even see something speak out or something. But
Yeah.
all was about mouse overs. Like when I'm going to do a tab and then come over and reset a traffic. So what is it going to show me? That was what. Yeah. Let's see.
So I'll go into those details in the next lecture. So what do you,
Sure.
but just shortly saying that, okay, the title element we give to things that come out when you hover over something, over an element, right? And that's and I'll show that in a bit more detail next time with these landing zones I was discussing, because the title element doesn't come out very well if you have to really hit a line only. But if you put a larger rectangle around it, then it comes out nicely. And that's exactly also then what we can exploit with screen readers. And today I'm quite glad I didn't have to do that, because then I will have to change browser for that. And we already had enough problems with taking a setup today.
No problem. Thank you.
Any other questions?
Yep. In most of the textbooks, the diagrams that we are dealing with are not in SVG formats. So it's a big challenge how to handle those things. Till now, we were thinking of just adding image descriptions and converting the diagrams which cannot be handled with image descriptions into tactile versions. But I think from the perspective of low vision students and with other disabilities, this SVG is very important. So
It is, and I don't know where your graphics are coming from. I mean, there are certain graphics which don't lend themselves to SVGs, right? Things like where you have an image of a landscape or of a piece of art, picture. Clearly, that doesn't really help. Which doesn't lend itself. But things, even if you only have say a schematic, say a setup of an experiment and things, even those things you can do with SVGs. You can include, for instance, small foreign objects, i.e. other images in an SVG, which then give you a way of structuring things and being able to expose some of that information. Now, as I said, I don't know where you have these images from, but it is a common phenomenon that a lot of the publishers in their workflows are not SVG ready.
Right.
So I've been talking to some of them for quite a few years now. So the ones we are really now working with are W.W. Norton, just to name a few, Elsevier and Pearson, but they're only now SVG ready fairly recently, and whereas others, simply they've got bitmaps in their workflows and they will have not the means right now to change them.
Okay, but even the things that we create in Excel, if we incorporate them into the main documents, is there a straightforward way to make them in SVG